My name is Jeff Kenvin, and I'm the Technical Director at Micromeritics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks can cause slides to advance more slowly than others, so logging off of your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I am pleased to introduce today's speaker, Professor Robert Ryu. Professor Ryu joined the Pennsylvania State University in 2008, where he is currently the Friedrich G. Helfrich Professor of Chemical Engineering and Chemistry. Rob has numerous awards, including a DARPA Young Faculty Award, an Air Force Office of Scientific Research Young Investigator Award, a National Science Foundation Career Award, and a 3M Non-Tenured Faculty Award. His group's current research focuses on the development of spatially and temporally resolved spectroscopic techniques for imaging catalytic chemistry, elucidation of reaction mechanisms in nanoscale systems, the development of solution calorimetric techniques to understand catalytic processes at the solid-liquid interface, and the design of active sites in metal-based catalysts with a particular emphasis on intermetallic and single-atom catalysts. Rob, it is an honor for me to introduce you today. We are so glad you could be here today to share your insights on intermetallics with isolated metal ensembles, define active site requirements, and dictate catalytic selectivity during semihydrogenation.
I'd like to start off by thanking Jeff Kenvin for the invitation and for Gemma from Micromeritics for the organization of this seminar. Today, what I'd like to do is tell you about a work that's been done in my group and utilizing intermetallics to help design isolated metal ensembles that ultimately define what are the active site requirements for catalytic selectivity during semihydrogenation. There's two stories I'd essentially like to tell you. On the left-hand side, I'd like to tell you the story about how nuclearity, or the size of the active site, influences catalytic selectivity during semihydrogenation. And on the right-hand side, I'd like to tell the story of how modulation of the composition of an active site further influences selectivity during semihydrogenation. Now, intermetallics are essentially an alloy, but they're a special type of alloy because they're single phase and they're periodic. They demonstrate long range order. And ultimately, that implies that the local composition is equal to the bulk composition in an intermetallic. Now, in catalysis, we are very familiar with utilizing alloys to control or understand how catalyst structure influences activity and selectivity. In most of these cases, though, we're using solid solution or random alloys. And in that case, it's difficult to define the exact location within the lattice that that second element occupies relative to an intermetallic where the location of that additional element is well defined. And I show this by example, cartoon example. On the left, we have a solid solution or a random alloy where you can see that the position of the red and blue spheres, which represent two distinct elements, is not well defined, and the local composition certainly does not equal the bulk composition. Where on the right, the story is completely different. The occupancy of the blue and red spheres within the lattice are well defined, ensuring that local composition is equal to bulk composition. To examine the influence of nuclearity and composition of intermetallics on semihydrogenation selectivity, we've chosen to use acetylene as our model compound. As you can see on the top, acetylene, the preferred reaction, is the hydrogenation of acetylene to ethylene, while avoiding the overhydrogenation of ethylene to ethane, and correspondingly minimizing or eliminating oligomerization of acetylene to butene or even higher carbon number products referred to as green oil. Now, the use of alloys to influence selectivity during acetylene semihydrogenation is not new. It has been studied for many years. And a recent paper has demonstrated that palladium-zinc alloys are advantageous from the standpoint of balancing both semihydrogenation selectivity and acetylene disappearance activity. Intermetallics have been used for a number of years in heterogeneous catalysis, and generally these are binary systems that are made up of two metals. The first metal is the active metal, generally a D block metal, known for doing catalytic chemistry, and the second metal is generally from the P block or the early transition metals that generally carries no catalytic function and serves as a diluent of that active metal. Now, that does not have to be rigorously true. The second metal could also serve a catalytic function, but generally the active metal is the dominant catalytic entity. So in this work, we're going to talk about two distinct types of intermetallics. The first one are binary intermetallics, where what we're going to do is look at palladium-zinc intermetallics, and we're going to subtly tune the composition of the intermetallic phase in order to demonstrate how that has stark impact on both catalytic activity and selectivity for semihydrogenation. The second class of materials that we're going to look at are ternary materials, where we're simply going to do is substitute in a coinage metal, either gold, silver, or copper, and demonstrate how changes in composition influence selectivity during this semihydrogenation reaction. So before we demonstrate any experimental results, it's key to look at the phase diagram for palladium-zinc. And from the phase diagram of palladium-zinc, there are a number of intermetallic phases, but there are two more important ones to highlight here. The first one is the beta-1 phase. This is a beta-1 phase that has really high palladium concentration, up to 50% or even greater of palladium, and it's referred to really as a high symmetry unit cell. The second one is more rich in zinc in terms of composition, and this is referred to as the gamma brass phase. This will be the predominant phase that we will discuss during the rest of today's lecture. But you can see it has a much lower palladium composition, only between 15.4 and 19.1 atomic percent. But what I will demonstrate is that subtly tuning that stoichiometry between 15 and 19 atomic percent will have stark impact on the catalytic activity and selectivity. So from here on out, I'm going to discuss only the gamma brass phase, and the next thing we need to do is describe that gamma brass phase. So the gamma brass phase is made up of four symmetrically inequivalent lattice sites. These are referred to as the cube octahedral, the octahedral, the inner tetrahedral, and the outer tetrahedral. Now, the unit cell is composed of 8 outer tetrahedral sites, 8 inner tetrahedral sites, 12 octahedral sites, and 24 cube octahedral sites, for a total of 52 atoms in the unit cell. The image up above is just half that, 26 atoms, to really demonstrate the uniqueness of the different types of sites. Now, at the lowest nominal concentration of palladium in the gamma brass phase, which amounts to palladium-8 zinc-44, it has been determined that all 8 of those palladium atoms occupy the outer tetrahedral site. Now, with a total of 8 tetrahedral sites all occupied by palladium, the question would arise is, as I tune the composition of the gamma brass phase, where do those additional palladium atoms occupy? So the question would be is, if I add 2 additional atoms to the gamma brass phase of palladium, what lattice position do they prefer? So let's first talk about how we make these materials. So these materials are made by a very simple solid-state diffusion approach. And we choose this approach over any other approaches because it really allows for tight composition control. And ultimately, that is what's most important to us in this work is ensuring that we can finely tune the composition of palladium in these intermetallic gamma brass phases. So after synthesis, shown on the left, you have a small ingot of your intermetallic material. We need to grind these materials and then re-anneal them to ensure that the thermodynamically stable surfaces are obtained after grinding. So here's a typical SEM image of what these materials look like. They're platelet-like, and that's basically just due to the fact of ball milling to increase the surface area of the original ingot that's formed. Now, from a characterization standpoint, there are some challenges associated with these materials. They generally have low surface area, less than 1 meter squared per gram, but that surface area is large enough that with enough material, we can carry out catalytic chemistry on these well-defined, compositionally controlled intermetallics. The sizes of these platelets range, in the micron range, and this tends to make them difficult to characterize by CO and hydrogen Chem Absorption. So after synthesis of these materials by solid-state diffusion, we need to characterize them to ensure we've achieved the compositional control that we're looking for. The technique of choice is X-ray diffraction with Rietveld refinement in order to confirm composition. So palladium-8 zinc-44 was synthesized and characterized by X-ray diffraction, and consistent with results from the late 60s, we demonstrated that all 8 palladium atoms occupy the outer tetrahedral site, as indicated by the site occupational factor being equal to 1 for these materials. So it turns out, by careful examination of the crystal structure of the gamma brass phase, what this leads to is that these 8 palladium atoms are isolated from one another in the lattice. So in palladium-8 zinc-44, only palladium monomers can be found. Now, if we increase the composition to palladium-9 zinc-43, record the X-ray diffraction pattern, and do Rietveld refinement, what we find is that the additional palladium atom has 3 choices. It can either occupy an inner tetrahedral site, an octahedral site, or a cube octahedron site. And what we find the preference from Rietveld refinement is for that additional 9th palladium atom to occupy the octahedral site. And the implications of that are demonstrated here, that by far the octahedral site is much more stable than occupation of either the cube octahedral site or the inner tetrahedral site. And ultimately, the implications of that, as you can see, is the palladium-9 will contain both monomers and trimers. Now, if we add an additional palladium atom to now have a nominal composition of palladium-10 zinc-42, what you can see is that that additional palladium atom, again, prefers to occupy the octahedral site, and the implications of that simply are now we have more trimer sites than monomer sites in the palladium-10 zinc-42. DFT calculations further confirm that, in fact, both palladium atoms in palladium-10 prefer to occupy the octahedral site over any other combination. And so the reason why there's much more data on this plot compared to the previous plot associated with palladium-9 is that effectively in the addition of 2 metal atoms to the gamma brass phase, these can occupy sites at distinct differences from one another, and we need to calculate all those possibilities. Now with DFT, that's challenging, but with cluster expansion models, we've been able to do that and basically show that the DFT calculated energies fall in the convex hull of the gamma brass phase and tuning of its composition. So XRD refinement, density functional theory, and also these cluster expansion models show that palladium trimers form both in palladium-9 and palladium-10. So this is the summary that for palladium-8, we expect to have only monomers of palladium, whereas in palladium-9, we will have both monomers and trimers, and in palladium-10, we'll have less monomers and more trimers. The quantification of that as a function of palladium atoms per unit cell is effectively, as we go from palladium-8 to palladium-9, we see this linear increase in the number of trimers from 0 to 2, and a decrease in the number of palladium monomers from 8 to 4. So what we've been able to do by subtly changing the composition of the gamma brass palladium zinc intermetallic phase is to change the nuclearity of presumed palladium active site. So before we can really examine these in catalytic chemistries, we need to assess the stability of these materials. Now, some of the challenges that I discussed on a previous slide related to low surface area and difficulties in characterizing these materials, we really resorted to density functional theory to specify for us the stability of these types of materials. So in doing surface energy calculations with DFT, we've been able to demonstrate that facets that contain these trimers are exposed and are stable and represent about 50% or so of the total surface area on palladium-9. And so it turns out that these 1, -1, 0 surfaces are those that contain the trimers, and these tend to be stable surfaces according to surface area calculations. If we look at palladium-10, probably as anticipated, the story hasn't changed. Again, a surface that exposes trimers is stable and predicted to be exposed from a Wolff construction, and so therefore we have both surfaces on palladium-9 and palladium-10 that contain these palladium trimers. So the other element of stability we need to verify is the fact that on these exposed surfaces where trimers exist, are they stable? And so we looked at this in a number of ways, and we looked at an exchange between palladium atoms residing on the surface and the exchange between palladium atoms in the bulk and on the surface. And relative to the trimer, what we find, for example, is the tetramer is over an EV or about an EV less stable than the trimer. If we increase the size of that cluster to palladium-5, it turns out, again, it's less stable, and now it's even farther less stable than the trimer. And if we go up to palladium-6, what we can find that it's over 2 EV less stable than the palladium trimer. So all of this seems to suggest that the surfaces exposing the palladium trimers are stable. So the summary from DFT calculations are the following. Palladium occupation in the bulk is favored in the octahedral site for both palladium-9 and palladium-10, and we've confirmed this with combined X-ray diffraction and refilled refinement. Surfaces that contain these trimers are low surface energy surfaces and therefore exposed on Wolff constructions. Any exchange to grow or reduce the surface exposed trimers appears to be unfavorable from DFT calculations. So now we'd like to ask the question, are the subtle changes in palladium concentration in the gamma brass phase catalytically significant? So on the left here is an example of palladium-8, where palladium atoms are isolated from one another. And on the right is an example of either palladium-9 or palladium-10, where we have these contiguous palladium trimers that have formed. So from these cartoons, we would certainly say, yes, by subtly tuning the composition of the gamma brass palladium zinc phase, we should see changes in catalytic reactivity. And so we're going to explore that basically through 3 sets of reactions. The first 2 that really focus on activity are going to be H2D2 Exchange on these monomers and these trimers, and then the hydrogenation of ethylene on these monomers and trimers. And to probe differences in selectivity between isolated and trimer sites, we'll use the semihydrogenation of acetylene in order to probe the influence of nuclearity on selectivity. So here are the first catalytic studies that are done. This is the H2D2 exchange, okay, on palladium-8, palladium-9, and palladium-10. And what you can see is this nice linear increase in the rate per area as we increase the number of palladium atoms in the gamma brass unit cell. As expected, as you move from palladium 9 to palladium 10, the activity doubles on a per area basis, consistent with the fact you anticipate a doubling of the number of trimers from palladium 9 to palladium 10. Now we've done some DFT calculations on this to demonstrate that in fact experimental results are captured by DFT, and so on palladium 9, we're able to measure an activation energy of around 50 kilojoules per mole, and theory returns the same value. Whereas on palladium 8, we find the activation energy is in a similar range, but slightly lower, and once again, DFT is able to calculate the behavior on the palladium trimer. So we want to move to a reaction that's a bit more demanding, and this is ethylene hydrogenation. And so what we've done is examined the hydrogenation of ethylene over 3 catalysts, the palladium 8, palladium 9, palladium 10, intermetallics, and then compared that with a palladium foil. And so what you can see from the graph here is that on palladium 8, the catalyst is completely inactive for the hydrogenation of ethylene. As you begin to add additional palladium, so palladium 9 and palladium 10, you can see from the blue data that the rate begins to increase and becomes a measurable quantity. Whereas then if we look at the palladium foil, it's very active, many orders of magnitude more active than any one of the intermetallics. Now a comparison between palladium 9 and palladium 10 here on the right, the top plot being palladium 10 and the bottom plot representing palladium 9, demonstrates that they have similar activation energies, and once again this doubling in activity on a per area basis as we move from palladium 9 to palladium 10. So this experimental data is all consistent with DFT calculations and the proposed doubling of trimers as we move from palladium 9 to palladium 10. And so what we have learned from looking at this data is that the trimer surfaces are active for the hydrogenation of ethylene, whereas the monomers are inactive for the hydrogenation of ethylene to ethane. And so this provides some impetus to further study these systems for semihydrogenation selectivity. So the first thing we did were DFT calculations with the group of Professor Janik at Penn State. And what he has demonstrated is that essentially the palladium 8 intermetallic is selective for the semihydrogenation of acetylene because in fact ethylene once formed would prefer to desorb rather than hydrogenate. And that's really demonstrated by the difference in the barrier for the hydrogenation of adsorbed ethylene to the ethyl intermediate versus simply just the desorption of the formed ethylene into the gas phase. Now, if we put palladium 9 on there, the story changes. And on palladium 9, because the difference between the semihydrogenation reaction barrier and the desorption barrier are more closely together in terms of magnitude, we suspect that the trimer sites will be less selective or unselective for acetylene semihydrogenation, and we'll see stark differences between subtly tuning the composition from palladium 8 to palladium 9. So in summary, we can see here, if we compare that with palladium 11, if we look at the differences between these two barriers, either the desorption of ethylene or the semihydrogenation of ethylene, as we know from previous experimental results, palladium is a very good, or contiguous palladium is a very good ethylene hydrogenation catalyst, and so the barrier to desorb is much larger than the half hydrogenation barrier. Whereas when we move to palladium-9, we can see that there is a switch in the order of these barriers, and we're able to desorb some fraction of adsorbed ethylene. But as we move to palladium-8, we see that selectivity for ethylene is even greater because of the stark differences in the barrier between desorption and half hydrogenation. So we wanted to examine this experimentally. In fact, are the DFT calculations correct? And so the way we've done this is to employ an isotopic tracing method where we isotopically label the ethylene with carbon-13 in order to be able to follow the fate of all the products that form. So in this case, we define two types of selectivities. The first selectivity is the intrinsic selectivity. So for the acetylene that's fed to the reactor, what is its selectivity to ethylene? But because we feed ethylene into the reactor with an isotopic label, we will be able to distinguish between ethane that formed from fed ethylene versus ethane that forms from fed acetylene. And so here that helps us define a net selectivity. And this net selectivity is ultimately the value of most importance when thinking about designing an industrial catalyst for this reaction. The higher the net selectivity, the better your catalyst is at hydrogenating acetylene to ethylene without further hydrogenating any added ethylene to ethane. So here is the intrinsic and net selectivity for palladium-8. And so a good hydrogenation catalyst would have similar intrinsic and net selectivities and also high. And so what we can see here is we're in the range of about 70% or so, and the difference between the intrinsic and net selectivity on palladium-8 is small, which basically demonstrates that palladium-8 is not good at doing ethylene hydrogenation, which is consistent with the observations we saw when we studied the ethylene hydrogenation reaction only. Now, if we look at palladium-9, there's a very stark difference. So palladium-9's intrinsic selectivity to ethylene is high. But as we look at the net selectivity, we can see the net selectivity is much different than that found on the palladium-8 sample. And you can see by the highlighted blue area that it actually goes negative. And so the expression for net selectivity allows for negative selectivities. And negative selectivities, as you would imagine, are bad. That means you are hydrogenating that excess ethylene that you fed into your reactor. And so you can see that the net selectivity, as you go to higher and higher conversions of acetylene, begins to decrease substantially. So this is great experimental evidence or proof that the DFT was right in the prediction that palladium-8 should be selective for acetylene semihydrogenation, and palladium-9 should be far less selective for acetylene semihydrogenation. So the experimental results so far have demonstrated a few things. Well, first, palladium-8 is composed of only monomers. It tends to be selective at a level of about 80% or so for acetylene semihydrogenation. The kinetics are far reduced in terms of the rate of disappearance of acetylene relative to a contiguous palladium surface. We've also learned that palladium-9 and palladium-10 contain strimers. These are much faster on a rate per area or turnover basis for both H2D exchange kinetics and ethylene hydrogenation kinetics. And this ultimately leads to these trimers being unselective for acetylene semihydrogenation. So if I take those two data points, palladium-9 and palladium-8, and I put them on a graph of the net ethylene selectivity versus activity, what we find is palladium-9 has a very low selectivity but very high activity, whereas palladium-8 has low activity but high net selectivity for ethylene. And so the question is there any scope for modulation? is there anything we could do, presumably to palladium-9, to influence the selectivity? We'd like to increase that selectivity. This is not an example of trying to optimize. We're just trying to understand if we can modulate activity and selectivity by tuning parameters of these isolated active sites. And so if we look at the palladium-9 surface, it is essentially composed of these palladium trimers and palladium monomers. And so is there anything we could do to actually influence the activity and selectivity of these surfaces? And so one thing we could think about doing, and what we have done, is we tune the composition of these trimers, or we attempt to tune the composition of these trimers. And so the way we've done that is by substituting one of the palladium atoms for a coinage metal. Here's the example of gold. And these are DFT calculations that essentially show that if you incorporate gold into the solid state synthesis of these gamma brass palladium zinc structures, the palladium prefers to remain in those outer tetrahedral sites, but the gold will occupy the octahedral sites. And so here is experimental evidence of this. Again, from Rietveld refinement, all 8 palladium atoms go in the outer tetrahedral site, whereas that one additional gold atom prefers to occupy the octahedral site. And so the implications of this are the following. What we expect to form in these systems are trimers that are composed of palladium, gold, palladium. And that palladium and the palladium atoms occupy the outer tetrahedral sites, whereas the gold, silver, or copper will always be found in the octahedral site, forming essentially these palladium M palladium trimers. So here is what the X-ray diffraction patterns look like for the various materials. Here are SEM images with EDS maps showing that the elements are distributed evenly throughout these materials, and that in fact we have created these ternary gamma brass palladium zinc systems that we were aiming for. So in order to test the influence of the coinage metal addition to the trimer site, the first thing we did was DFT calculations of the mechanism or the energetics for semihydrogenation of acetylene. And what we can see is if we compare the two selectivity determining steps, the semihydrogenation of adsorbed ethylene versus the desorption of ethylene, we can see that when we add the gold atom into the octahedral site, the activation energy or the apparent barrier for the semihydrogenation reaction increases relative to that to what we calculated on palladium-9. So this tends to imply that the gold added to the palladium trimer should increase the selectivity for acetylene semihydrogenation. And this is summarized nicely in this bar graph where we compare the barriers for these two rate determining steps, selectivity determining steps. And if we compare palladium-9 to palladium gold palladium, we can see that the barrier for that semihydrogenation step represented by the green bar has increased relative to that on palladium-9, while the red bar representative of ethylene desorption hasn't changed much between those two catalysts, and we would expect selectivity to increase to ethylene on the palladium trimer containing the gold atom. So here are two sets of experimental results. One is for a gold containing and silver containing trimer. And what you can see is that the intrinsic selectivities are very similar amongst one another. They don't differ too much from the palladium-9 trimer, but what one does see starkly different between the coinage metal containing trimers and the palladium-9 trimer is that the net selectivity for both gold and silver is much higher than what was observed on palladium-9. And this is just indicative of a higher barrier to the semihydrogenation of adsorbed ethylene to the ethyl fragment. So again, what we've been able to do is not optimize, but modulate the net selectivity by the addition of the coinage metal, either gold, silver, or copper not shown, to have intermediate values of selectivity compared to both palladium-8 and palladium-9. And so this really summarizes the results between the experimental and computational agreement with regards to both activity and selectivity. So far what we've been able to demonstrate is that we can make these gamma brass palladium zinc catalysts. Palladium-8 gamma brass materials expose only monomers, whereas palladium-9 and palladium-10 expose both monomers and trimers of palladium. We've demonstrated that these trimers can be modified compositionally, by the addition of a coinage metal, and that modification of composition leads to changes in selectivity during acetylene semihydrogenation. And what we've learned is that monomers are active for semihydrogenation of ethylene, but they are inactive for the hydrogenation of ethylene. So what we'd like to do is to use the palladium-9 gamma brass system as a model to study and completely describe the mechanism of ethylene hydrogenation. So as a reminder, DFT predicts that monomers will desorb ethylene rather than hydrogenate it, and the trimers have a preference to hydrogenate ethylene. And this is captured nicely by really summarizing the selectivity defining steps from a DFT standpoint, where on palladium-8, there's a stark difference between the barrier for semihydrogenation versus the barrier for desorption. And the difference in those barriers decreases substantially when we form the palladium primer in the palladium-9 system. And so the theory and the experiment agree with one another in terms of palladium-8 being a poor ethylene hydrogenation catalyst and palladium-9 being an active hydrogenation catalyst by the data demonstrated here on the right-hand side, where at all temperatures, palladium-8 is effectively zero activity, and for palladium-9, 10, and 11, the activity for ethylene hydrogenation increases. So what we believe we will be able to do with the trimer-containing systems is we will be able to rigorously characterize the reaction mechanism of ethylene hydrogenation. And the predominant reason for that is these trimers are isolated from one another. And what that does is reduces some of the chemical complexity that arises during the hydrogenation of ethylene. And this chemical complexity has really been captured already in the open literature by those performing density functional theory calculations coupled with microkinetic modeling. And one of the primary challenges associated with modeling ethylene hydrogenation is that there are just a vast number of possible coverage conditions that are encountered as we change temperatures and ratios of partial pressures of ethylene and hydrogen. And so this work captures that effect through the calculation of how the Gibbs free energy of adsorption changes as we change the coverage of either ethylene or acetylene on these surfaces. And in the middle here, these graphs clearly demonstrate that the adsorption energies change substantially as the coverage of either acetylene or ethylene increases. The second challenge, which really is manifested as a coverage effect, is the fact that generally simple single or dual site type models fail to describe the complexity of the sites and how they may interact with one another. And so this is captured nicely again in theory work combined with experiment, where the theory really struggles to capture the experimentally measured reaction orders, both in ethylene and hydrogen, as demonstrated on the right. The advantage of the trimer sites present in palladium-9 and palladium-10 is the fact that they are isolated from one another. And so this really allows us to consider, or need to consider, only a finite number of coverage scenarios in the microkinetic modeling of ethylene hydrogenation. And so we're going to use DFT calculated barriers for both the formation of transition state and then adsorption energies in order to be able to calculate the rates of individual steps. And in this microkinetic modeling, we're going to be able to converge upon steady state rates associated with the hydrogenation of ethylene over these trimer sites. And so experimentally, what we find studying the hydrogenation of ethylene is that the reaction order in hydrogen is around 1, and the reaction order in ethylene is right around 0, and the activation energy is about 68 kilojoules per mole. Now, if we consider both independently a single site model and a dual site model with no consideration of coverage effects, what we see very quickly is that while the reaction orders are in good agreement, we're way off on the activation barrier. So again, this consideration of coverage effects, again, rears itself and demonstrates how important it is to consider. And so what we find in these isolated sites is that, these isolated trimer sites, is that the trimer site can only accommodate 2 ethylene molecules. And we can clearly see this from the graph on the left-hand side, that as we begin to absorb a 3rd ethylene molecule onto this trimer site, the energy of adsorption just begins to increase and becomes positive. We've also demonstrated at the temperatures at which we run this reaction that ethylene dehydrogenation cannot proceed on the trimer site. So we do not believe we'll ever see any formation of an ethylidine intermediate or anything where ethylene has been dehydrogenated. So what that ultimately allows us to do is to essentially write out the complete reaction network for the hydrogenation of ethylene on these trimer sites. And so this figure really culminates the entire number of reactions that are possible for ethylene hydrogenation on these trimers. It amounts to about 70 or so different reactions, and from each one of those reactions we calculated with DFT adsorption energies and associated barriers in order to form a microkinetic model. And so we've been able to demonstrate with this fully detailed model where we've explicitly written out every possible reaction that can happen in every possible coverage scenario, we are able to capture the experimental data. What also comes out of the model, which would be difficult or impossible to recover from experiment, is the associated coverages with the various trimer and monomer sites that exist on the palladium-9. Now the monomer sites are completely covered with adsorbed ethylene, where the trimer sites, what we find is that the outer atoms of the trimer are covered with either a pair of adsorbed ethylenes or an adsorbed ethylene and a adsorbed ethyl fragment. Turns out that by degree of rate control analysis, what we discover is that really the adsorption of hydrogen onto that central atom for these trimer sites that are occupied with C2 fragments on the edge atoms of the trimers is really the rate controlling step here. So I'd like to finish off this talk by acknowledging a number of people. I certainly couldn't do it on my own. Initial funding for this work came from the National Science Foundation as part of a GOLI with ExxonMobil. So I'd like to thank Professor Michael Janik and Dr. Haran He for all the DFT calculations, and Dr. Randall Meyer from ExxonMobil for his collaborations during the NSF funded of this project. The work is currently funded now by the Department of Energy, and I'd like to thank my colleagues from Penn State for their help with the cluster expansion model calculations related to the stability of the palladium gamma brass intermetallic phase. And so with that, I'd like to stop. Thank Jeff again, thank Gemma, and answer any questions if there are.
Thank you, Rob. I'm opening up the chat for everyone's questions now, and we already have a few. Rob, this is really a wonderful talk on creating materials where you gain a tremendous amount of fundamental knowledge. Why did you select this system?
Yeah, that's a good question. We originally started with nickel zinc, and nickel zinc has the same gamma brass structures with slightly different compositional bounds, but the same crystal structure as the palladium zinc phase. And what we ultimately found during that work was that if we were to tune the composition within that gamma brass phase space, that we would be able to form these monomers and trimer systems. Unfortunately, with that system, it didn't quite work because of the sort of oxidative instability of nickel zinc in those intermetallics. But noticing that palladium zinc was identical to the nickel zinc system in terms of the presence of that gamma brass phase, we thought we'd have a better opportunity and a better chance in order to stabilize these trimers in the palladium zinc surface than the nickel zinc surface. So really the motivation was the failure to try and do this with nickel zinc, because we were more interested in nickel zinc as a selective hydrogenation catalyst because it potentially had applications applied because of the inexpensive nature of nickel and zinc compared to palladium.
You showed really nicely acetylene hydrogenation, ethylene hydrogenation. On the monomer system, what's the commercial significance there?
Honestly, Jeff, I don't think there's a lot. The commercial catalyst that's used for acetylene semihydrogenation is an extremely dilute palladium in silver material, and so the amount of palladium that is in that material is pretty small itself. I do think that if we could come up with a very rigorous and reproducible method to make these as small nanoparticles, there could possibly be an opportunity, but I think synthetically that's a real challenge compared to the kind of real simple approach to make the current palladium silver industrial catalyst. So I don't think these things are ever going to show up in any commercial reactor, but like you mentioned earlier, I think they're really great systems for just kind of fundamentally understanding how the size and the composition of an active site influence both activity and selectivity.
You mentioned early on the difficulty with Chem absorption on these systems, particularly something like CO Chem absorption that's been so commonly used with palladium. Can you comment on that a little bit? And are there other, potential things, possibly spectroscopy, that could be used?
Yeah, so this is something we have spent a really long time trying to get figured out because, as you mentioned, Jeff, CO Chem absorption, infrared spectroscopy of adsorbed CO, these are really kind of the bread and butter of our field in order to characterize samples outside of, just reactivity examination. To date, we've just really had no success with any of these more standard characterization tools simply because the materials are of very low surface area. I wrote 1 meter squared per gram, but in reality they might be even as low as 0.2 to 0.4 meters squared per gram. It really depends on that whole physical kind of grinding step that we have to do. Other spectroscopies such as infrared, again, we we struggle with the fact that they're low surface area, they're high absorbing materials. I mean, they're dark gray to black powders. And then the other reality associated with them, even if we could get those techniques to work for us, the absorption of a probe molecule, which is generally very strong to a metal like CO, is really weak in this case. And so, absorption energies now are not from, the DFT calculated range in pure palladium of an EV or greater. Now they're on the order of 0.3 to 0.4 EV. So that's promising from the standpoint of these catalysts may also be resistant to poisoning by CO, but it's detrimental and they're very difficult to characterize using, a really standard probe molecule like CO. Now, we have tried other measurements too, ones that are maybe not as commonplace in the catalysis field as Chem Absorption or infrared spectroscopy, but we've tried low energy ion scattering, and, for us, we've unfortunately not had much success there, and I think that's associated with not having the proper ability to reduce the sample correctly before doing the LEIS analysis. I should say, though, other groups working on intermetallics, such as Cyrus Larson's group at the University of Tennessee, have successfully employed LEIS to measure surface composition of similar intermetallics, nickel, gallium in this case. So LEIS is probably the best case scenario for us, and we just have to really learn how to properly prep the sample before inserting it into the LEIS spectrometer.
So I feel compelled. This is a question from me that I have to ask, and that is, I always remember perhaps your former advisor always would recommend we should never forget ethylene adsorption for Chem Absorption. Is there any potential for using ethylene for Chem Absorption on these systems?
Yeah, again, I think so. I think similar challenges remain. I think one of the advantages of using, so I've done a lot of ethylene Chem Absorption on platinum, not palladium, but and the problem that you run into there is even at room temperature, you can get dehydrogenation of the adsorbed ethylene, and that can cause problems with hydrogen being emitted to the gas phase and influencing your volumetric measurements. Here, we certainly won't have to worry about that problem. These trimer sites and monomer sites certainly do not dehydrogenate ethylene, but again, I think it will be an issue of surface area and just having good enough resolution in that measurement to distinguish between adsorption and possible leaking of the instrument. But we would like to try that. We now have the ability to do low temperature Chem Absorption, and so we will give that a shot eventually. What we'd like to do ultimately is really be able to make these in the really tight compositional controlled fashion we're able to do with bulk metals in the form of nanoparticles. And we're making some progress on that, but we're not 100% there. But I'm confident once we're able to get there, then these more typical measurements probably will work for us.
So we've got a question on the topic of the synthesis, and you're using grinding to get to the final catalyst. How do you ensure there aren't any impurities from the grinding balls in your final catalyst?
Yeah, so that's a great question. And it's something we spend a lot of time trying to confirm that we have no impurities in our sample. And ultimately what it comes down to is a lot of X-ray diffraction analysis to make sure that there is no phase in there that is not consistent. There's basically no Bragg reflections there that are inconsistent with the gamma brass phase. We spent a lot of time looking at XPS of these samples, so it's not a surface-sensitive technique, but it's probing more closer to the surface than something like X-ray diffraction, which is probing the whole bulk. And so those two measurements are the primary ones that we use to confirm the as synthesized ball milled material has no impurities. And then probably for me, personally, the most convincing measurement we do are really careful ICP-MS analyses of the dissolved grinded material, looking really across the spectrum of what impurity possibly could be within those materials. So, I mean, those are the methods, the approaches we've used to eliminate impurities. Are there ppm, ppb level impurities? I would never say no, absolutely not. There never is. It's just palladium and zinc. There possibly could be. But what we do find is that the influence of ball milling with time on the reactivity has very little influence on the catalytic results. So maybe one would anticipate if you ball mill for longer periods of time, you would deposit a greater amount of impurities, and that impurity, most likely would have a detrimental effect on catalysis, but we don't see that.
You presented some very nice data on selectivity and conversion. Do these intermetallic materials, do you observe any significant or induction or deactivation, when you start or toward the end of reaction during the on-stream time with these materials?
Yeah, so I think like any other catalyst that you run ethylene hydrogenation on, there is, some level of deactivation. Certainly on the contiguous palladium samples that we've looked at, so just pure palladium, the deactivation is much greater than what we observe in the trimer-containing systems. There is a deactivation period initially in the trimer systems, but that activity stabilizes pretty quickly. And so the next question that could come from that was, well, does that deactivation and that initial adsorption of either acetylene or ethylene lead to the restructuring of the catalyst, breaking up of the trimers, growth of the trimers? Again, we don't have an experimental way to really verify that breakup or that growth, but DFT demonstrates that even with adsorbed ethylene in the calculations, there's really no propensity to either break up or grow those trimers. Those trimers are extremely stable on the surfaces of which they're exposed, and the gas environment does not appear, as long as it's a reducing gas environment, the gas environment does not appear to influence those trimers either breaking up or growing. And so we think the deactivation is really just associated with some level of deposition of carbon.
We've got time for one last question, and this pertains to your DFT calculations, your colleagues' DFT calculations. Can you comment on what tool set they used for performing those DFT calculations?
Yeah, the DFT calculations are done within VASP. I apologize, I can't quote exactly what functionals were used, but they were done by my colleague, Mike Janik, who's really skilled in the art and science of doing these calculations. And then the microkinetic modeling was done in a home-built MATLAB code. So those are really the two methods that were used in order to both come up with the DFT calculated barriers and to complete the microkinetic modeling.
That's all the questions we have time for today. If we haven't been able to get to your question, one of our application team will be in touch with you shortly. Rob, is there anything else you'd like to mention today?
I'd just like to say thanks again to Micromeritics. Thanks to you, Jeff. Thanks to Gemma. Thanks to all those that listened. And if you're interested in intermetallic systems, reach out to me. What we're really looking for is partnership with folks who are skilled in the art of synthesis of these materials, because we believe through our current funding from the DOE that there are just an innumerable number of intermetallics, both in the binary and ternary phase space, that may turn out to be really exciting catalysts.
Great. Thank you, everyone, for participating in today's webinar. If you have any feedback for us, we would be grateful if you could complete the survey which we distribute in our follow-up email. Hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again very soon. Thank you and have a great day.